So we're just showing, so I think we'll get started again. Keep ourselves on schedule. And the whole purpose here is just to illustrate that the reservoir of cation exchange capacity that's in the soil, clays, and organic matter is so much bigger than the very small amount of dissolved cations that are in the soil water. Okay. So we can test nutrient content, but we can also evaluate the share of the ion exchange capacity that's occupied by certain elements. We've done something already. We've calculated the cation exchange capacity. That's the total amount of positive charge that's retained by 1 kilogram of dry soil, right? Well, now we can do a very related calculation, also likely on the test, so this is good. And that has to do with, well, what percent of the cation exchange capacity are kind of especially cations that I might be interested in, all right? Or that soil scientists have tended to be interested in. And this is a measure that soil scientists use as kind of a basic measure of soil fertility. And it's actually used to classify wholly different groups of soils from one another. So it's used in soil classification. All right. So there's a particular interest in this share of absorbed elements or share of charge that's absorbed onto soil because of through cations, that's represented by atoms that aren't what we think of as acidic cations. So we're not interested in the amount of hydrogen that's stuck to the soil. We're not interested in what we think of as other acidic cations like aluminum or iron, manganese. We're interested in ones that are what we think of as the basic cations. And so here are the acid cations and the basic cations. And so there's this related to CEC, related to cation exchange capacity, a measure of what percentage of the positive charge that is stuck to the soil is positive charge due to these 4 elements, the basic cations: calcium, magnesium, sodium, and potassium. It's used in soil classification, and it's a basic measure of soil fertility. That's how it's used. Inherent soil fertility in a way. And so it's got a name. It's called base saturation. All right? So the base saturation, it's the share of the cation exchange capacity, which is due to those 4 elements, the charge of those 4 elements. The share of cation exchange capacity that's due to the charge on those basic elements. So we're going to measure the cation exchange capacity of the soil, which is the total amount of positive charge that a hunk of soil can retain. We're going to put that in the denominator. And on the numerator, we're going to add up all the charge that's due just to the 4 basic cations. And we're going to ignore the charge of anything else. All right? So it's the shared CEC that's provided by the basic cations. And so here's how we do it. We got our cation exchange capacity in the denominator. This is all the charge that's stuck to the soil, all the positive charge stuck to the soil. Denominator. And then in the numerator, we're just going to count up the centimoles of positive charge that's just due to the 4 basic cations. Basic means of gauging soil fertility. So let's look at our example. We've seen this one before. We've calculated the cation exchange capacity. We've got 1 kilogram of soil, and from it, we've measured this amount of positive charge from all these different cations, right? And we figured out that we had 25 centimoles of positive charge per kilogram of soil, because we just added up the positive charge. Well, now we want to calculate the base saturation. So how are we going to use this 25 centimoles of positive charge? That's going to go where? It's going to go in the denominator. And what's going to be in the numerator?
5 from magnesium.
Yeah, the positive charge from the basic cations. And this is a pretty simple list. In real life, there would be many, many more, but this is we're simplifying things. 4 of these we're going to add the charge up with them, but one of them we're going to ignore. Which is the one we're going to ignore?
Hydrogen.
Hydrogen. So we're going to ignore hydrogen. We're going to add up all the other charges because those come from the basic cations. That's going to be the numerator. And so here we go. Essentially 22 divided by 25. And so our base saturation is 88%. Now, note, this is very key. In cation exchange capacity and base saturation, are we counting up numbers of atoms?
No.
No, we are not counting up numbers of atoms. If you don't watch yourself, that's what you're going to think you have to do. That's the way to mess this up. You are not counting up numbers of atoms. What are you counting up instead?
Moles of charge.
You're counting up amount of charge. And we're counting up centimoles of charge. Yeah. So in base saturation and cation exchange capacity, it's about charge. It's not about numbers of atoms. It's about charge, not about numbers of atoms. So make sure you write that down. All right? Okay? Okay. Now let's start talking about this thing called pH. Okay? All right, so changing gears. Let's find out what pH is, okay? And here's the deal. The formula is weird, and yes, it's true. More hydrogen ions in solution means a lower pH, means more acidity. That's the part that you just got to get. More hydrogen ions means low. It means higher. More hydrogen atoms means lower pH. More hydrogen atoms, lower pH. Same thing. Get used to that, and then everything else is pretty easy. Okay? When we're measuring pH, we're measuring the amount of acidity versus alkalinity in the soil solution. And pH is simply shorthand for the number of dissolved hydrogens that are present in the soil water. It's just shorthand for it. And this is very interesting. This is where some of the beautiful simplicity comes in. We like to think that there are win-win situations all the time, right? Win-win, win-win. But for hydrogen ions and for hydroxyl ions, this is amazing. It's a zero-sum game. And what I mean by that is that if one goes up, the other will go down. It's not a matter of under certain circumstances it might go down. No, if one goes up, the other will go down. It doesn't matter whether it's fresh water. It doesn't matter whether it's seawater. Okay? When one goes up, other goes down. And that is just true. It's true on Earth, it's true on Mars. All right? Under acidic conditions, hydrogen ions are more present. Hydroxyl ions are less present. Opposite under alkaline conditions. When one goes up, the other goes down. There's no ifs, ands, or buts about it. It's just remarkably true. Okay? There's some simplicity there. Okay? There's no special circumstances to try to remember. So here's where we're going to make a connection between the concentration of hydrogen ions and pH. And might be easy to get intimidated by all the zeros on the left or by the scientific notation in the middle, but check it out and you'll actually see how elegant this is, all right? If I've got 1/10 of a mole of hydrogen ions per liter, 1/10 of a mole doesn't sound like a lot, right? 1/10 of anything doesn't sound like a lot. 1/10 of a mole of something is a huge amount, right? Because a mole is so big. So if I've got 1/10 of a mole of hydrogen ions per liter of solution, I've got a massive amount of hydrogen ions in there, okay? And so I've got a really low pH, and that means that I have an extremely dangerous solution, all right? An extremely dangerous solution because it's so acidic, okay? 1/10 of a mole, same thing as 10 to the -1. And look what the pH is. The pH is kind of it's the exponent. All right? pH is an exponent. If I've got 1/100th of a mole, not as acidic, all right? I've got 10 to the -2 is a way to say 100th of a mole. pH is 2. Still really acidic, still really dangerous, but not as dangerous. And so look how this works. Here's 10 to the -7th, all right? pH is 7. So it might be easy to kind of get intimidated by pH. People try to get intimidated by it because they think they need to be. This table kind of like, it shows you that it doesn't have, there's a pattern here, okay? That is a pattern here. And now we got another column, and we're adding the hydroxyl column. And note, when the hydrogen ion concentration is 10 to the -1, the hydroxyl ion concentration is 10 to the -13. Sure. When the hydrogen ion concentration is 10 to the -2, the hydroxyl concentration is 10 to the -12. Okay. When one goes up, when one becomes, here's a lot of hydrogen ions, here's not a lot of hydroxyls. I'm getting fewer and fewer hydrogen ions, right? But as I do that, I'm gaining more and more and more higher concentration of hydroxyls. So there's a zero-sum game. When one goes up, the other goes down. And notice, do you notice something that's always true? 14, right? Multiply the one by the other, and you'll get 10 to the -14. Okay? So, and here's this side at the very top, okay? With pH, what are we doing? We are paying attention to the exponent, all right? A logarithm basically is an exponent. The log of 10 to the 7th is 7. The log of 10 to the 9th is 9. The log of 10 to the -7th is -7. So if I want the formula for pH, pH is equal to the log of the hydrogen ion, but because my exponents are negative, I'll put a negative in the front of the whole thing and I'll end up with a positive number. A logarithm is an exponent. And that's how this works out mathematically. But it's just this very elegant, incredibly simple relationship between two competing things. It couldn't actually be more simple than this. When one goes up, the other goes down. Okay. How do we end up using this thing? Well, On the right hand, excuse me, on the bottom, we've got various different pHs. Okay, here's the pH 4.5, acidic. All right. Then we got pH 8. Here's neutrality, pH of 7. pH at a pH of 7, what is true about the number of hydrogen ions versus the number of hydroxyl ions? They're equal, right? When hydrogen ions have this concentration, it happens to be the same concentration of hydroxyls. Do hydrogen ions and hydroxyls cancel each other? Like, can you ever have at neutrality, you'd think, well, maybe they cancel each other. They don't cancel each other. They're both present. Yeah, they're just present in the same concentration, the same amount. All right? So here's where the concentration of both of those things are 10 to the negative 7. And more acidic on the left, more alkaline on the right. And we've got obviously a lot of these important plant nutrients. And sometimes these things are narrow, sometimes they flare. When they flare, what that means in this diagram is that the element tends to be more plant available at that pH. Okay, so the degree of flaring, that's about plant availability. Kind of on average, right? There's going to be certain soils that for some reason it's not going to be exactly like this. This is on average. Yeah.
Does temperature affect that? The availability is that affected by soil?
Temperature does affect the availability of nutrients. Sometimes in very early spring, or early enough in spring, it's cold. The above ground part of the plant, the air might be a little warm, but the soil itself isn't warm yet. The soil itself is cold. So the above ground part of the plant is growing maybe a little faster than the roots are. The root can't really kind of keep up. And in that sense, you have the elements might not be, well, it's actually a little bit different. In that case, the elements might be present, but the plant hasn't been able to keep up in its ability to gather them. So temperature effects can show up in a bunch of different ways. Inherently, no. But I think in that example, you've got the fact that the soil temperature is colder. It's inhibited the ability of the plant to develop its root system. And so until that soil warms up, the plant itself is going to just have a harder time getting at what's there. But it doesn't mean that it's not there just because it's cold. It's there, but the plant can't keep up with the lower part of the plant can't keep up with the demand from the upper part.
Would you adjust when you add your fertilizer based on the or does it's not that big a deal?
Some farmers will add a little bit of starter phosphorus early in the season to put in the soil a lot more soluble phosphorus than would otherwise be there. The phosphorus is there, but they add more to make it that much more available so that they avoid an early season and usually temporary phosphorus deficiency. That oftentimes, in a lot of cases, the plant might be effectively deficient in phosphorus at the beginning, that early part, but that there ends up being no yield detriment to the plant by the end of the growing season, even if you don't apply the starter phosphorus. So some people do that just because they want to, but in a lot of cases it's not necessary. So what this is saying is, at some pHs on average, there's not going to be a lot of a certain nutrient. At other pHs, there might be too much. So you can't really manage your fertility without managing your pH. there's a sweet spot for pH and nutrient availability, luckily, that's fairly universal. It's kind of right in here, all right? Just slightly acidic. It's where we get kind of nice plant availability of most of our nutrients. If we get excessive, then we might get a toxicity due to molybdenum. You can't really get a toxicity due to calcium, I don't think. But if we get too acidic, we can definitely get a toxicity due to aluminum. Notice how aluminum is really not plant available at all until you get below about a pH of 5.5, and then it rapidly becomes available, and you can get an aluminum toxicity. So we want to stay above a 5.5 unless you've got some kind of specialty crop. And generally, the sweet spot is kind of in the slightly acidic region here. So controlling your pH is a big part of soil fertility. Making sure that your plant nutrients are kind of maximally available. Get the pH dialed in. It even affects things like nitrogen fixation. The bacteria that do that like to have a particular pH environment. So what are some pHs that we want? All right, so for alfalfa establishment, we like to have neutrality. Tobacco likes it fairly acidic, all right? Even more so for potatoes and sweet potatoes, all right? But most agronomic crops, pH of about 6.5 would be great. Okay, new question. How is it that soils lose their ability to supply nutrients? All right, so remember, here are the nutrients that we know that our plants have to have. And notice that these things are mostly ions. Some negative, some positive. And ions, they can dissolve in water, they can stick to charges in the soil. They can also be transformed into other things. The nitrogen cycle, for example, Dr. Tour is going to talk to you about that. I think it's Dr. Tour is going to do that. All right? Lots can happen. There's a lot of ways to lose nitrogen. And if something's dissolved in water, well, what's great about that is it's the stuff that's dissolved in water, that's the stuff that plants can get. Okay? That's a good thing. If it's stuck to the charge in the soil, well, that's good too, because it might not be available for plants right then, but it will be available in the future. Well, what's bad about stuff being dissolved in water? Well, if it's dissolved in water, when the water moves, the ions will move with it, right? You can remember that this is very relevant to what Brian was telling you guys earlier today. You might, if you got a lot of nitrate in your soil water in the fall, if you don't do something to catch it, it's going to be gone by the springtime. Might have been there in the fall, but by the spring, your plants are not going to be able to catch it. So what do? Plant something in the fall early enough so that that plant can get to it and pull it up into the biomass before it leaches away. All right? And according to the work that Dr. Weil's done at the university, plants do that work of catching that nitrogen in the fall. They don't do it over the course of the winter. They're not that active in the winter. By the time the winter comes around, the stuff that they haven't caught is gone. So that's why you want to plant a cover crop pretty early. The rule of thumb in Maryland is you want to plant it around Labor Day. That's how that plant has enough time to catch that nitrogen before it leaches away. All right? So if it can dissolve in water, it's great because the plant can get it. But what's bad about that is that it can leach. Now nitrate is, it's not that sticky. It's got a single negative charge. There aren't a lot of positive charges in the soil for negatives to grab onto. It's got a very weak negative charge, and so nitrate is going to leave really easily. Phosphate with that highly negative charge, it's much more sticky. It's 3 times stickier. So what it can do is it can stick to the few positive charges that are in the anion exchange capacity of the soil. The difficulty for phosphate is that there aren't a lot of positive charges that are resident in the soil, not nearly as much as the negatives that are there in the clays and the organic matter. So there's a limited number of positive places for this anion to stay. And if you've added a lot of phosphorus over time, at some point you're going to saturate the soil's ability to hold on to any more phosphates. And when you do that, this ion that normally is pretty sticky because it's highly charged can begin to leach, just like nitrate can. So this is one of the reasons why we want to avoid the over-application of phosphorus and soil phosphorus levels that are too high. Because if those soil phosphorus levels are too high, there ain't any more capacity for the soil to hold any more. And this thing that normally was so sticky no longer is. And it'll leach just like the nitrate does. So we can lose stuff from our soil through leaching. We can also lose stuff through volatilization, because we can take something that was either in ionic form and therefore dissolved in the water or stuck to a soil solid, and if we turn it into a gas, it'll literally just bubble out. All right? Nitrogen is really good at that. So here's a situation where in low spots of this field there was waterlogging. And because there was waterlogging, there was the exclusion of oxygen. After the soil was waterlogged for just a few days, the bacteria went through the oxygen that was present, and there wasn't any more left. And when the bacteria were done breathing the oxygen, they then went on to breathe other things. And the first thing they're going to breathe after they breathe oxygen is they're going to breathe nitrate. When they breathe the nitrate, they change it. You know, we take oxygen and we turn it into CO2, basically. They breathe nitrate and they turn it into nitrogen gas. And that happens once they've run out of oxygen. So they've run out of oxygen because there was waterlogging. They've breathed the nitrate that was present, turned it into nitrogen gas. It's gone. And if the plant wasn't killed by the low oxygen situation in the soil because of the waterlogging, the plant will end up with a nitrogen deficiency because the nitrate that had been there isn't there anymore because it was volatilized and turned into a gas. All right? Dr. Tour is going to talk to you more about the nitrogen cycle, but you can remember this example. All right? So we can lose nutrients by leaching. We can lose nutrients by volatilization. Nutrients can interfere with one another too. Too much of one thing can get in the way of the plant being able to take up something else. All right? And so here are just some ions that will interfere with others. And what's interesting is that, you know, some positives, if you get too many of one, that are positive, they can interfere with another. So just something to be aware of. Generally, plants can sort things like this out. It has to be kind of an extreme situation for there to be a problem to develop. But it's one thing that can happen. So we can leach stuff that we want to have. We can volatilize stuff we want to have. If we get our chemistry too out of balance, they can interfere with one another. But another thing that happens in Maryland, and this is just a totally natural process, over time, because rainwater is itself naturally slightly acidic, okay? Actually more than slightly acidic. The natural pH of rainwater is about 5.5, okay? And that assumes no smokestacks at all. If you got smokestacks and, you know, nitrates and sulfates being put in the atmosphere, the natural pH of rainwater, the pH of rainwater is no longer natural. It gets really low. That's the acid rain problem. that even with no smokestacks at all, the natural pH of rainwater is going to be about 5.5. All right? And so what's going to happen over time, even if there's no smokestacks, soil, if you've adjusted the pH to be closer to neutral, over time, that pH is going to become more and more acidic. It just naturally happens because that's the way rainwater is. And when that happens, you take yourself out of the sweet spot that you put yourself in with the lime application, and you get yourself, you're put back to a more natural acidic condition. Forest soils are naturally acidic, usually. Now, how does that soil acidity originate? There's a lot of ways that we can make soil more acid, okay? One of them, the one I've already mentioned, is that bullet point in the middle, rainfall. The natural way that it happens is as rainwater falls through the air, it picks up some CO2. The CO2 every once in a while will break apart and produce a carbonic acid. And that's how we get rainfall that's got a pH of 5.5. If there's smokestacks around, well then we get some nitric acid added, we get some sulfuric acid added. But plants themselves will put acidity into the ground. If a plant is exuding hydrogens, what are those hydrogens going to do? They're going to knock off some of the cations that the plant might want from the soil solids, right? Puts out enough hydrogens, some calciums are going to come off and the plant can get it, all right? So plants are constantly exuding things. Some of the things that they're exuding are acids. Organic matter itself, as it is oxidized, will release acidity. Dr. Tour is going to talk about that. That's just part of the nitrogen cycle. Organic nitrogen, as it is oxidized, produces acidity. So when you go from organic nitrogen to nitrate, acidity is released. It just happens. Anytime, and also the two bottom ones, anytime you've got an aluminum atom that's kind of locked up inside a soil mineral, it gets exposed on the surface of the mineral or dissolves into the soil water, the aluminum will literally rip water molecules apart. It'll hold on to the hydroxyl part and it'll let the hydrogens go free. That's called hydrolysis. Sulfur does something similar. So are there a lot of ways that, many of them natural, that acidity gets introduced to the soil? There are many ways. So soils naturally acidifying is completely normal. And this is why when your granddaddy added lime in 1950, was that good enough for right now? No. He had to add lime again in 1955, right? Then your dad had to do it in 1960 and 1965. Now you got to do it. Another way you can mess up provision of nitrogen is that you can have soil material that's so high in carbon that the plants effectively get robbed of the nitrogen that's there. So what we've got here is we've got a continuum of carbon to nitrogen, all right? On the far side, we've got materials like sawdust, about 400 carbons to every nitrogen that's present. On the right-hand side, we've got something like microbial biomass, where for every one nitrogen atom, only 10 carbons are present. So there's a lot more nitrogen here, a lot more nitrogen concentration in bacterial biomass than in sawdust. All right? Now, if you were a bacteria and you were growing in sawdust and you were trying to raise your family, how precious would a nitrogen atom be? Incredibly precious, right? Because you're searching through atoms and only 1 in 400 is the one that you need. And think of what bacteria are. Bacteria are basically protein packets, right? Nitrogen is an obligate part of every protein. So if you're a bacteria and you're trying to grow your family, nitrogen is incredibly precious, all right? So if you have a soil environment where there isn't enough nitrogen around, the bacteria are going to be scavenging it up so quick that what should be available as nitrogen, available for plants, isn't going to be. Because the bacteria are going to be vacuuming it up faster than it gets released for the plants. All right? That's this process that Emily mentioned to you guys earlier called immobilization. All right? Immobilization is when the soil environment is so enriched with carbon that the nitrogen becomes so precious that the bacteria outcompete plants for it. Now, if you get away from this over-enriched environment with carbon, and you get around to about here, okay, well then nitrogen ions become sufficiently abundant that demand by bacteria is usually exceeded, and there's enough nitrogen around that's dissolved in soil water that plants have access to. Okay? How do we determine nutrient deficiencies? A couple of different ways. All right? Now, there isn't always a toxicity for every nutrient out there. Not all nutrients will have a toxicity. I don't think there's any such thing as a phosphorus toxicity. So take this right-hand side with a bit of a grain of salt. This is not always true. This is kind of here for illustrative purposes. But the left-hand side is always true. You can't have too, you might not always be able to have too much to kill something, but you certainly can have too little. All right, well, one way to kind of get a fuzzy idea about whether you've got a nutrient deficiency or not, you could do a soil test. All right? You're testing the soil. You're wondering how much is there. That's not the same thing as a crystal clear picture of how abundant or deficient a nutrient is in your plant, because that's actually what matters. Right? We can usually say, okay, well, if I've got this certain level in the soil, well, that's probably going to be a problem. But if you really want to know it's a problem, you do a tissue test, okay? The soil's a little bit fuzzy, usually good enough. If you want a picture perfect, clear idea, you do a foliar test. And sometimes, if that deficiency is really aggravated, you can actually see visual symptoms in the plant. All right? The plant is going to be screaming at you because of the way the tissue looks. But a lot of the time, there might be a deficiency, but it's relatively mild, and you can't tell necessarily by looking at the plant. That's called hidden hunger. All right? Foliar testing, you don't necessarily need foliar testing if you're looking at your plant and you're seeing the sign of a nutrient deficiency. But a foliar test can be really helpful to determining if, it kind of looks okay, but let me check, to determining hidden hunger. Here's a nice example. Forget about the middle row. This corn doesn't look so bad, right? It's plenty green, it's growing. If you didn't have this test row where you had applied 100 pounds of nitrogen per acre at that rate, you might not necessarily know that you didn't have a problem, that you had a problem. So this is an example of hidden hunger. We're beginning to get the beginning of kind of a clear sign of a nutrient deficiency down here on these lower leaves. You notice you're not really seeing that down here. The lower leaves are still pretty green. But if you were kind of doing a quick look, you might miss that, and you might think, my plants look pretty good. You'd have no idea that they actually could be a lot taller. So here we're kind of right at the ragged margin between hidden hunger and kind of something that's bad enough that it becomes visually obvious. If it's visually obvious, it's kind of nice. It's kind of a nitrogen deficiency. It looks like a browning and a yellowing for corn, at least along the middle vein. For potassium, it's opposite. It's on the leaf margins. A phosphorus deficiency oftentimes will show up as a purpling, right? And magnesium here, you can get stripes. You can sometimes get stripes too with an iron deficiency, so that this is kind of an indicative thing. How easy is it to kind of use a couple pictures from a guidebook and be like, oh yeah, I got this. And feel like you can march into any field and kind of, be the authoritative consultant. No. It's gonna take working with somebody who's seen this a lot, right? But it can be done.
How often do you recommend doing like a foliar test for ones that you don't notice like those symptoms of? Like do you do that every couple of years or like what do you recommend?
We do foliar testing, at least the Ag Nutrient Management Program out of College Park. When we write a nutrient management plan for somebody, we will require a foliar test once every 3 years. And this is because of MDA requirements, but it's kind of informed by science. We'll require a foliar test for fruit-bearing crops. For the grain crops and for the vegetable crops, we just have a soil test. However, you might be wondering, is it legit to take a foliar test of a corn crop? Absolutely it is. And we have a really wonderful test called the corn stalk nitrate test that you do at the end of the season. So you've grown your corn, you've applied the fertilizer that you did, and what you can do is you can do this corn stalk nitrate test, and it'll tell you whether you dialed in your nitrogen application basically just right, or whether you might have added too much. And you can use that knowledge to gauge how much you ought to use next year. So that's a tissue test that could be done quite regularly on a corn crop by somebody who's really interested in saying, okay, well, am I over applying? Let me do this corn stalk nitrate test, let me see. But normally we do the tissue tests for the fruit crops. One key difference is that some elements, if there's going to be a nutrient deficiency that's going to show up, the nutrient deficiency will show up in the oldest leaves, the leaves that are lower. Other nutrients deficiencies will show up near the upper part of the plant. And this is kind of cool. It has to do with the inherent mobility of the nutrient within the plant. If the nutrient is really mobile, well, what the plant can do is it can say, you know what, my most important leaves are at the top, so I'm going to move, if I'm limited for something, I'm going to move it out of the bottom and bring it up to the top, right? Those are the mobile nutrients. And so if we're going to see a deficiency with those, we'll tend to see that deficiency on the lower part because those nutrients have been moved from the bottom up. But there are some nutrients that aren't mobile. Once they're in, they're stuck in place. So the bottom part of the plant might look just fine because at the beginning of the season the plant was small, the demand wasn't great, and so it had enough nutrient for that. But as the season goes by and there's this limiting nutrient, the plant's getting bigger, needs more, the deficiency will show up at the upper part because that's a nutrient that can't be moved. Yes, ma'am?
So, trying not to get too off track here, but my brain does this sometimes. So, like, let's say there are different nutrients that kind of pair with each other, right? So, I've been in a field and I've seen a calcium deficiency, I think it was, and it was showing up as aluminum toxicity when I ran or high aluminum levels when I ran the soil test. Is that?
what I've heard is that one of the reasons why you get an aluminum toxicity is the plant will take up the aluminum thinking that it's a calcium and will try to stick it in a calcium place. But of course it doesn't work.
So maybe.
So what you say might make sense. It looks to you like a calcium deficiency, and it is, because what ought to be calcium is not, and it's not there because aluminum's been taken up in its place.
Okay. So they just move in a similar way through the plant, and that's why it's.
That would be my guess. I am not an expert in that part though. And you'd have to talk to a real expert.
I have to look back and see. I know it's an area where typically we're putting dolomitic lime down, but dolomitic lime still has a pretty high calcium volume to it.
Yeah,
So I'd have to check the stool samples to see for sure. But those were two things that I noticed. I'll have to see.
Thanks for that. Thanks for that question, that connection between calcium and aluminum. That's great. Yes, ma'am.
Okay, I got one question. Is there a resource that would say, that would answer that question for her, that says, you have an aluminum deficiency, and you may have calcium? Is that resource exist, where those relationships have been fleshed out between these nutrients?
I'm sure. I mean, I've got, you see, I want to see what's here. Where'd it go? This table. Yeah, this doesn't include aluminum, but presumably aluminum would go up here. Aluminum in excess would result in maybe a calcium deficiency, according to the, what's your name?
Megan.
Megan. Right.
And the website is probably.
Yeah, I got the website right there. Right.
Right.
This does, very good. So check that out.
Yeah.
So the question here, the question is it because of charge? Is it because of ionic radius? Part of it is charge, because you've got positives that are kind of faking and getting in the way of the positive that you want, right? So part of it's charge. But different ions have effective different radiuses, just like different atoms have different radiuses, right? And so if you've got two atoms, they're different, two ions are different, but they're both positive charge and they're about the same size, and one can easily substitute for the other.
That's sort of the periodic table where you have the chemistries. So if you have aluminum, affected calcium, then anything in that family right around that would probably, you could guess would also affect calcium.
I think that's a great hypothesis that makes tons of sense. At this point, we just have to look at some science, you know, some tests to see, but obviously it makes tons of sense. Yeah.
Someone can do that situation.
And it probably has been done. I mean, that table there got generated by somebody. So, interestingly, the idea that in a plant, something of similar charge and similar size could get substituted or kind of mess the plant up, that's actually exactly what happens in a clay particle as it's being formed. In that process of isomorphic substitution, it will result in a clay particle ending up with a negative charge. What happens in isomorphic substitution is you've got normally there might be an aluminum that gets stuck someplace with a positive 3, but instead of the aluminum getting stuck, a positive 2, like a calcium, gets put in its place. Yeah, and because there's not as much positive where we would have put it, we end up with a negative charge, and that's how clays get this negative charge. So the mechanism is the same.
Magnesium solution, drop all those calciums.
Well, yeah. So if you have too much, you can have a magnesium toxicity. That's why we have these what we call serpentine barrens, because we've got soils that are so high in magnesium because the parent material is high in magnesium. What that does is it kind of creates a calcium deficiency that makes it hard for unspecialized plants to thrive there. You gotta have plants that can deal with this excessive what we would think of as normally an excessive magnesium content.
I'm sorry, just to take that one step further. In her situation, she had too much aluminum, so she didn't have enough calcium. So how do you get the plant to dislodge the aluminum and take up the calcium?
You raise your pH.
Okay, so.
You raise your pH because, I'm gonna go way back here. Here we go. Aluminum only starts to become appreciably soluble a little bit below 5.5. So if you raise your pH up, aluminum just ain't gonna be, it's not gonna be dissolved. It'll be there, but it'll be there in solid form. It won't be dissolved. So you raise your pH and you make it so the plant can never get confused.
But the main issue is gonna be, and correct me if I'm wrong, like in this situation, it was a corn plant, and that tissue cast was kind of like an afterthought at that point, because applying lime or applying, you're essentially trying to rectify that for the next cropping season, not like the current crop that's there.
So you're shooting this year.
Yes. Yeah.
Yeah, because if you do have a low pH, if you're in, 4.5 to 5 pH where that soluble aluminum is going to become an issue, it's going to take time to, take care of that pH issue. So if you were to apply lime tomorrow, it's still going to take 3 to 6 months to neutralize that acidity and bring that pH up. It's not an instant solution.
There's no situation where the plant would release that to pick up what early.
No, because like I said, it's pulling, soil solution, water from the soil solution, and what's going to be soluble in there is what's going to be soluble in there, and that's what the plant's going to take up.
Thank you for
Yeah, that aluminum has a charge of +3. That aluminum ion, once it's in, it's not going to be movable. It's going to be stuck in the plant. The plant's not going to be able to move it out. Look at all this progress we're making. This is great. So mobile nutrients deficiency on older leaves, immobile nutrients deficiency on younger leaves. All right? And then, so in general, we can say that certain elements are going to tend to be immobile in a plant, so therefore the deficiency is going to show up on the upper leaves. And certain elements are going to tend to be mobile, and so their deficiencies will show up on the lower leaves. Kind of nice and elegant. It's one of these ways that you can use to kind of distinguish what's what, because sometimes the deficiency on the leaf will look the same, but you got to look on where on the plant it is, and you can get the idea. But this is not something that you can become expert in 15 minutes of looking at some pictures, right? So can the concentration of a nutrient be too high? Yes. Toxicity, but it's only a problem with some nutrients. But in soil water, nutrients are ions. If they're too abundant, the soil could become too salty. And as we've seen before, high concentrations of one nutrient can interfere with another. Deficiencies and toxicities can occur even if soil test levels are good or optimal. That seems kind of funny. How could that possibly be? Well, if you've got a drought, it's just harder for nutrients to flow towards the roots because the nutrients are dissolved. There's not a lot of water there, so the water is moving nice and slow. And so you could get a deficiency because the plant simply can't get to the nutrients that are dissolved because they're not flowing very fast because there's not a lot of water to carry them. You could also have potential salinity problems because your soil water is kind of too concentrated with too many ions. The soil might have plenty of nutrients, but what happens if the soil is waterlogged? Well, if it's waterlogged, all the pore space is filled with water. No pore space is filled with air. In that case, the bacteria that are around are in just a few days, about 3 to 5 days, are going to use up the oxygen that's dissolved in the soil water. And when that's gone, the plant roots can no longer breathe. All right? And so the plant roots themselves could die. If the waterlogging issue is resolved, well, because of volatilization, you could have lost some nitrogen, right? And so you could lose some elements because of volatilization. You could also, because of a lack of water and what bacteria do, you could end up having too much of other things produced by bacteria, like sulfides that are toxic to roots. There's obviously a lot more to this. We're not going to go into the weeds and the details of it. But waterlogging can be a big problem, even if your soil test levels are great. All right? Cold soil could restrict below ground growth, like we've talked about already. All right? And then you might have great test levels of a certain nutrient, but if your pH is too low or too high, effectively that might curtail the availability of the nutrient. All right, so just other pictures of nutrient deficiencies. Sometimes nutrient deficiencies show up in a stunting of leaves, right? Like with boron. So there's a lot more to it's a whole little universe. Okay. Oftentimes, and this is a nice statement here. Oftentimes, a deficiency early in the season will sort themselves out. Here's something from an ag educator in Illinois. Unfavorable conditions for crop growth mean that observing some deficiency symptoms should not be cause for immediate alarm. If deficiencies continue after growing season conditions improve, confirm a deficiency before trying to correct the problem. Since visual symptoms are sometimes not clear-cut, it could be beneficial to collect affected plants and conduct tissue nutrient analysis. This is a nice summary of what we've talked about. All right, well, what can we do to maintain fertility? Get ourselves in the sweet spot. And then neutralizing soil acidity. How do we do it? What I'd like to do now, Alicia or Emily, is switch to the other PowerPoint. This PowerPoint that you're looking at now goes through raising the line, basically goes through.
The one we just did was 145, or 145. This one goes till 230.
All right.
Oh, can you make sure you click it? Okay, go ahead.
All right. Okay. So we're going to start talking about adjusting pH. Before we do that, a real quickie. It's important to be able to calibrate a fertilizer spreader. I'm not going to talk about that here. The University of Maryland has some guidance on that that's pretty easy to find on our website, but you can also check out some of these things. All right? It'll be more fun. We don't have to spend time doing it. Okay. Let's talk about optimizing pH by alignment. All right. How much should be applied? Well, in theory, we've got to know what we want as our target pH. Otherwise, what are we adjusting it towards? We also need to know what's our actual pH that we're starting at, right? Well, how much distance do we have to go? And then, remember what cation exchange capacity is. Cation exchange capacity, that's essentially the reservoir that can hold positive charges. It also means it's the reservoir that's holding hydrogen ions. And remember that the pH that we measure in a soil, that's the concentration of dissolved hydrogen ions. And remember that what's dissolved in the soil water is a mere fraction of the amount of stuff that's in the massive reservoir that's actually stuck to the dirt. Right? So we want to know what the pH is, but we also need to know how much stuff is actually sticking to this massive reservoir. Because remember, these things are in equilibrium. There's what's stuck to the soil is interactive with what's actually in the soil water. And if you're going to adjust your pH, you can't be only paying attention to that little fraction that's already dissolved. You've got to deal with this massive amount that's waiting for you to take care of that's stuck to the soil itself. That's in theory. In practice, you got to ask some more questions. Because when you buy liming material, are you automatically buying what you might think of as like the ideal liming material? If you pay tons of money, you are, right? But chances are, all liming material gets mined and created somehow. Some of it's going to be better than others. Some of it is going to have more neutralizing power inherently. Some of it, and depending on its quality, some is going to be ground more effectively than others. What if I had a massive block of, what if I needed to neutralize a field of them, and I was traveling around in Florence and I saw Michelangelo's David, right? This big, gorgeous block of marble, a lot of it too, right? Tons worth of marble, right? Lots of liming power in there. So I'd pick it up, put it on the airplane with me, and we travel back to Maryland, get back to my field where I need to raise the pH, and I just take the statue of David and I just plunk it down in the middle of the field. I got tons of neutralizing power on hand. How's it going to work? It's not going to work, because what I've got to do is I would have to do something horrible. What would I have to do to that statue if I wanted to line my field with it? I'd have to grind it up. Yeah. Okay? Don't try that with the David in Florence. Okay? So the other thing you got to be thinking about in the real world is, is this thing ground up enough? If I throw pebbles of limestone into my field, that's still not going to be good. So we've got to pay attention to this, because this is kind of the fundamental stuff, but then we've got to pay attention to the details. All right? The details have to do with what's the inherent chemical quality of what I have, and then what's the details of the grind. Because if it's not ground up well enough, it ain't going to work. All right? So I apologize to you, but determining lime recommendations is more complicated than you want it to be, because liming materials are not perfect. Okay? Have a nice day. All right. So because they're not perfect, you need to take into account the imperfections of your purchased lime. Okay? And you need to take these things into account, but you've also got to keep in mind the basics. What's your target? What are you starting with? How much CEC do you have to deal with? All right. So there's something there called the lime requirement. And what that does is it assumes perfectly ground, pure lime that's just chemically ready to go for you, right? No part of it's inert, right? That's the lime requirement. You're dealing with like the ideal world, all right? And then we have the thing that's the real world thing. That's the lime recommendation. How much of the real world stuff, given what you've got to do you actually need to put on the ground? All right? So we're going to do this in two parts. First, we're going to figure out a lime recommendation, which is saying, well, here's my situation. I've got this starting pH. This is the pH that I want. This is my cation exchange capacity, basically. That's going to be great. That's the lime requirement. Okay? But we're not done. Then we've got to take the details of the actual lime source we have, and we've got to include that in the calculation. And then we're done. Okay? Yes, ma'am?
When you get a soil sample, like I run mine through Spectrum, and you get the buffer pH, are they already taking into account CEC, or?
Yes, they are. And what they're going to do is, if they give you a lime recommendation, you're going to get a lime recommendation from them, right? And that's probably based on the buffer, pH. Otherwise, they wouldn't do it. Okay? There's a bunch of ways to deliver a lime recommendation. The official way in Maryland that we deliver a lime recommendation that the university offers doesn't involve the buffer pH. It involves your starting pH, your target pH, and then things that the university considers kind of equivalent to your CEC, which is your soil texture and geologic province. Okay? They're trying to get at CEC that way. They don't do the buffer method. They are toying with the idea of doing it, and it wouldn't be a bad idea. Okay, so we're going to do this in two parts. All right, now here's the lime requirement part. This is our ideal world, and kind of looks complicated enough. All right, but look at the assumptions that this graph is based on. Even this ideal world scenario. What is the assumption about the starting pH in this picture? The assumption in this picture is that we are starting off with a pH of 4.5, and then we need to adjust accordingly, right? And then it's very flexible. It says, well, if you want to adjust to 5, well, you're going to apply us a different amount of lime. It depends on what the cation exchange capacity is, right? If the soil doesn't have a lot of ability to hold cations, then we don't have such a big reservoir we have to deal with. But if the soil has the ability to hold a lot of cations, then there's this massive reservoir of hydrogens that's stuck there. And we've got to neutralize some of those things or get those away, right? So we're going to have to add more material in that case, all right? And there's some assumptions about kind of the cation exchange capacity associated with certain soil textures. And then, of course, well, we could adjust to a different final pH other than 5. We could adjust to a pH of 6.5. In that case, well, we've got to add more. And depending on what the soil texture is or what the cation exchange capacity is, we might have to add a lot more. So do you see how to interpret a graph like this? We know what we're starting off with. Will this graph work if you're starting off at a pH of 5? No. This graph works if you're starting off at a pH of 4.5. All right? Okay, so let's determine the liming recommendation. This is not the real world, or I'm already forgetting my terms. I think this should say the lime requirement. Take your pencil. I apologize to you. Take your pencil and cross out the C and put a Q in. The liming requirement. Take that C and put a Q. Do it in two places. Sorry about this. Okay. So, let's see. What do we need to know in Maryland? We need to know the results of our soil water slurry test. We need to know the soil texture and whether we're in the coastal plain or not. That's essentially what the university is using to decide kind of what your CEC probably is, right? Here's the coastal plain. If you're on the east side of I-95, consider yourself in the coastal plain. If you're on the west side of I-95, consider yourself that you're not. We're going to see how this works in a second. All right, and so we're going to get a tabular lime requirement halfway through, and that assumes an ideal liming material, and it assumes a uniformly fine grind. Maybe it's okay that those are recs and not requirements. So here's an example. We want to lime a corn or soybean field. Here's our current pH, it's 5.7, and here's our target, it's 6.5. And let's say that we're located in the Monocacy Valley. Where's the Monocacy Valley?
It's not in the coastal.
It's not in the coastal plain, right? Okay. So we know our initial pH, we know our target pH, we know where we're located. And here's this, if you type in UMD space SFM-5 extension probably, you'll come up with this document, right, which is the university's current way of providing a lime recommendation. All right? And you're going to get this table. And let's see how this is going to be used. Well, here's our initial soil pH, okay? This table is a little bit more universal than that graph we saw. That graph had started, it was only about starting off at 4.5 pH. Here, we have a bunch of different pHs we're starting off at, all right? And then up at the top, we've got various soil textures and various places that we are in Maryland, okay? And, but then here, look at this table. This table is only good for what? It's only good for a target pH. So I guess that previous slide that we had with the graph, it was only good for a starting pH of 4.5. This one's only good for a target pH of 6.5. So these things are specific. Let's see how to use this. All right? So here's our target pH. We can use this table because our target pH is the appropriate pH for this table. Here's our starting pH, 5.7. Our texture is a silt loam, all right? And we are in the Monocacy Valley. So we're in that column. We're at the right table. We know the row that we're going to be in. We know that we're over here, and now we know we're in this specific column because we're not in the coastal plain. We're outside of the coastal plain. And so that means how many pounds of ideal liming material are we going to want to add per acre? 3,000. Okay? So we go to Tractor Supply. We buy whatever liming material we want, and we put down 3,000 pounds of it. Correct or false?
No.
Why false?
Well, it's for the duration of the soil test, so it's over the course of 3 years. Right?
That's a detail too, is that when we provide a lime recommendation, soil tests in Maryland for nutrient management planning purposes are good for 3 years. So does this mean that we should apply 3,000 pounds per year
No.
for all 3 years?
No.
No.
1,000 pounds per year, like it's.
You could put 1,000 pounds per year, you could put 3,000 down, right? Now there's another caveat coming up about how much you should apply at any one time. That's coming up. Well, what's the problem with just going to Tractor Supply and buying liming material, whatever it is, and putting down 3,000 pounds of it?
It's not fair in line.
It's not going to be enough, because why?
It's not a perfect line.
Because you're probably not buying perfect lime. This table assumes perfect lime, right? It assumes perfectly chemically pure stuff, and it assumes that it's perfectly ground, all right? Neither of which your real world product will be, okay? So we're halfway through here, okay? We figured out the lime requirement. We have yet to figure out the lime recommendation. All right. So if our liming material was and notice what it says here. This is about assuming a total oxide content, right? Pounds of acre of total oxide. So if we've got this perfect, pure liming material, this is how much we'd add. So if our liming material was 100% calcium oxide and magnesium oxide, and it was uniformly ground to a very nice fine particle size, we'd apply 3,000 pounds per acre. But chances are the material that you've purchased isn't chemically pure, and it's not perfectly ground. Therefore, we have a little bit more work to do. In fact, we know what we're going to have to do. We're going to have to apply a little bit more than the recommendation says, because we're dealing with something that's less perfect. All right, well, first let's figure out how chemically perfect this stuff actually is. And we've got to look at the product label, all right? And you're either going to find something on the label that talks about total oxides, or it's going to talk about the calcium carbonate equivalent. Okay? You're going to find that on the label. What's the total oxide content and what's the calcium carbonate equivalent? And we've got a second question to ask then. How ideal is the grind? We've got to determine from the product label both the percent of this ground material that will pass through a sieve with really big holes. Okay? And we've got to determine, the label will tell us, the percent of the material that will fall through a much smaller hole size in a sieve. Okay? And then what we're going to do is we're going to take that data and we're going to calculate something called the fineness factor. All right, so I've got this term here, the full pass. This is the percentage of the stuff that will pass through both sieves, the big and the small sieve. If it passes through the small sieve, that's really good. That means that I've got it, that portion is ground very nicely, right? That's the full pass. But what about the stuff that's big enough to pass through the large sieve size, but not big enough to pass through the small sieve size? That means that that's been ground, but not as effectively, right? It's been ground, but not as effectively. Will Michelangelo's David go through the sieve with large pores? No. It's not useful. So what we do, therefore, is we totally ignore the portion that won't even pass through the big sieve. We'll totally pay attention to the portion that passes through the small sieve, but we'll only partially pay attention to the stuff that goes through the big one, but not through the little one. I've got a picture of that. So we've got these particle sizes, for a certain mesh size. Okay, we've got a small sieve, we've got a big sieve. Here's the stuff that passes through the small stuff, the small sieve. It's very nicely ground. It's all going to be effective, and it's all going to be effective within a few months. Then we've got, that's our full pass. Then we've got our stuff that won't go through the fine sieve, but it does go through the larger sieve. And this is the stuff that's going to be effective for us kind of in the longer term. Our partial pass. And then we've got the stuff that is sufficiently big that it doesn't even go through the whole sieve, the large size sieve. And that's basically kind of gravels of limestone. It's just not going to help us. All right? So we're not going to pay attention to that. And so we're going to pay attention. So in our calculation that has to do with the fineness factor, we're going to pay attention to all the stuff that's here, the full pass stuff. We're only going to pay attention to about half the content of the partial pass because it's just going to take longer for it to be effective. Will it all eventually be effective? Yes, but not in the time horizon that we're thinking that we want to have our lining material work. So our fineness factor is going to be the full percentage of the full pass stuff, but only half of the partial pass stuff. Does that make sense?
Hell no.
It's just that this stuff is a smaller particle size, so it's going to react faster. This is the stuff that's a larger particle size, so it's not going to react as fast. So we don't give it as much weight.
So what units are you measuring this in? Like grams?
It's just a percent.
Okay.
Yeah.
So is this theoretical or like can it be calculated for like each bag of lining material you buy?
The label is going to give you 2 pieces of information.
Okay, so this is all coming from the label.
This is all coming from the label.
Okay.
Yeah. They should have done this work for you already.
All right.
Yeah.
That makes it a lot easier.
Now, one thing that can be a little frustrating is that different manufacturers will use different sieve sizes. So some of them, their small size sieve might be a different size than others, right? So you just do the best you can. You just do the best you
So
can.
for eggshells, I see that practice long ago. I thought I never saw it before, but people use eggshells for their vine applications. So that means that they should not be used because the particles are quite high or big.
We just have to see some information to see if it works. I mean, in one dimension, they're pretty thin, right?
Yeah,
But the
actually
other,
I see big sizes.
yeah, I mean, I don't know how quickly it'll take for that to, the question is, at some point, you might have something that limes the soil, but it doesn't even lime the soil as quickly as rainwater is depositing acidity. In that case, you're always going to be falling behind. It's going to help, but you'll always be falling, and I just don't know the answer to that. I put eggshells down on my ground because I give it to the songbirds. The songbirds need that calcium to build their eggs. So I take eggshells and sterilize them, then I put them out and by the end of the day, the eggshells aren't there anymore. The songbirds have taken them up. There's lots of reasons to put eggshells in. So that's good stuff. So the grind affects the fineness of the lime. This is just justifying that idea. If it goes through 100 mesh means that in every inch there are 100 spaces. So the bigger the mesh size number is, that's the smaller the holes are. So if we're dealing with really small holes, because we've got 100 partitions per inch, well, check it out. This stuff is effective really fast in raising the pH, right? But if we're talking about fewer partitions per inch, well, we're talking about bigger particles, and we're talking about it works, but it takes longer and it might not be as effective. Because even though it's neutralizing, is it even keeping up with the natural acidity dumped from rainwater? Yes, ma'am.
This is information on the manufacturer's label.
Say it one more time.
This is information that is available on the manufacturer's label.
Yes. Otherwise, it's not useful to you.
So the manufacturer would say, if you need to add 3,000 pounds of lime, pure lime, this is how much of our product should cost. Wouldn't they say that on there?
Maybe they do. They're more likely to do that if you're buying something at Home Depot and they know that the average consumer does not want to be bothered with the fineness factor, right? And have to figure all this out.
Well, no one does.
So, but if you're talking on a more kind of industrial scale where people are kind of used to thinking about this because this is how it's done, then this information would be on the label. We're going to see an example of a label in a second. In fact, some of this information is available for certain lime sources on the internet.
Yeah, if you go to, MDA maintains a list of basically any registered lime product available for sale in Maryland. And it'll give you the oxides content, so calcium oxide and magnesium oxide. So it's like we're talking about the recommendations are in total pounds of oxides. And then they also give you, the percent that'll pass through a 100 mesh sieve, a 60 mesh sieve, and a 20 mesh sieve. And I mean, I just, that list is available. I just pulled it up. So, that is going to be on any label that should be, any label that should be for sale in Maryland.
Yeah, I hate to sound really dumb, but
I sound dumb all the time, so don't worry about it.
Let's clarify. 100 mesh is very small.
That's correct. That's
It's the
correct.
larger, the lower the number, the larger the hole.
That's correct.
Okay.
Yeah. A 1 mesh would equal a size of 1 inch can pass through. So what should our application rate of purchased material be? All right. So now this should say Q. This is our requirement, our lime requirement. And we're going to multiply it by 100% divided by the total oxides of what we purchased. This is going to be on the label. All right, and you'll see an example of the label in a second, and Brian is absolutely correct. It's on the website. It's on the website. And then we're going to multiply it by 100%, and we're going to divide by that fineness factor that we figured out. So put a Q here, folks. Sorry about that. To be corrected for next year. I've gotten away with that for so many years. That's embarrassing. And so, if on your label you're not given a % total oxides equivalent, but instead you're given a calcium carbonate equivalent, nothing changes. You're just going to use the calcium carbonate equivalent that they gave you. It's all going to work out. So here's what we got from the table that we looked at earlier, right? Here's what we got for the label for the purity. Here's what we've gotten from the label from the grind. All right? Now here's an example of one of these spots on this website, and there's the website, okay? And so let's say that your product is MG lime from the WRC, all right? So you looked it up, you found it, WRC MG lime. Here's our calcium oxide equivalent. Here's our magnesium oxide equivalent, okay? Here's different sieve sizes, all right? So what's our total oxide percent? Well, I'm gonna add those two up and I'm gonna get 43%, all right? In this case, I'm calling full pass the stuff that goes through the 60 mesh sieve. And then the partial pass is the stuff that went through the larger sieve but didn't make it through the small sieve. All right? And that's this amount. Went through the large sieve but didn't make it through there. That's my partial pass. I'm going to multiply by 1/2. My fineness factor comes out to 87%. So about 87% of this is going to be ground effectively for me. Pulled that right off the label, and this label is available from this website. Maybe you've got a source that isn't on the website. Maybe, but there's a label and it's going to have this information if it's a useful product. So my actual liming rate is going to be the lime requirement. Put a Q there. That's 3,000 pounds of my ideal material per acre. I'm going to multiply by 100% and divide by the total oxides of the product, which I got for that product from the website that I referred you to. And then we're going to multiply by 100% and we're going to divide by the fineness factor for that product that we determined from the sieve. And so we get that much purchased material should be applied per acre. You did it. Good job. A couple caveats. Is somebody actually going to be able to apply 8,019 pounds per acre instead of 8,017 pounds per acre? Probably not. All right? So, let's just make this, let's give ourselves realistic precision, right? Something like 8,000 pounds per acre.
So can I help
Yeah.
me out? So is it 3,000 pounds is the actual, recommendation? No,
So
so
that was the
requirement.
requirement
Yes.
from the chart for the,
Yes, and so
to
then,
change the pH.
okay, then you do the math. So the 8,000 is actually the recommendation due to the wide label.
Exactly right.
Okay.
Yeah.
all right,
Due to
now-
the fact that your liming material isn't perfect.
Yeah.
Yeah. you're going to end up adding more. You will always end up adding more than the lime requirement tells you, because your product is never perfect, unlike your spouse. Yes, ma'am.
Hate to ask this question, but will we have to, for the exam, will we have to run through the similar calculation?
Conceivably. In my experience, when I took the test, they really didn't ask hard ones. There are going to be some calculations that that you're going to get to see tomorrow that seem pretty tough, that have to do with like sewage sludge and everything, and they're actually not that bad because it only involves multiplication. And those questions didn't show up on the test that I took
When did
So-
you take the test?
last year.
Most recently?
So I don't think that it's maybe this could be on there.
I mean, it's important to understand regardless.
It's important to understand regardless.
But I'm just, Newman's calculating this.
Yeah. And here's the other
Well,
beautiful thing.
There's there's a rec on the soil test, and then, yeah, we do our own on Newman.
You may or may not be aware, there is a piece of software that is a nutrient management planning tool that the University of Maryland Extension uses. Anybody can use it. The cost to purchase a copy is minimal, all right? And that computer program will generate a liming recommendation for you automatically, assuming that you've entered things like what the soil pH is, assuming that kind of the crop that that it knows you want to grow, and therefore the target pH, assuming an oxide content, okay? That's an input into Newman that you have to specify. But you can do it by hand based on based on this SFM5 document, the table I showed you, and kind of this stuff. Or you can do it in the Newman program, right? And kind of does it nicely and elegantly for you. Yes, ma'am.
I apologize, I got confused, changed all our RECs to REQs. So, what is the recommended amount versus the requirement? This is the recommended amount, that's not the 3,000 pounds then?
The requirement.
There's the lime
The
requirement.
requirement for the soil itself to change the pH, and
That's
then,
the 3,000.
yes, ma'am, and then that's our recommendation for the actual product based on all these other
Factors.
factors.
Based on
Thank
the
you.
legal
Thank you. The right word.
So to make this PowerPoint slide correct, you should take that little C at the top, and you should make it a Q.
Except on that one chart where we got that 3,000 pounds, that's the recommended.
No,
No,
that's
that's
the
the
requirement.
That 3,000 pounds, that's the lime requirement. That's assuming that you've got perfect material. How much should you put down? You get that from the table.
Then I'm lost, you can explain what is the
I can-
common recommendation?
After this, I can come back and I can tell you about it.
The last number, the number he just erased, is our recommendation. If you came to me and asked me how much you should buy, that's what I'm gonna recommend you go buy based on the very first requirement of 3,000 pounds, and then all this additional information with the sieves and whatever.
You just said that the actual line rate is the actual line rate is the recommended.
The actual liming rate is the recommendation.
Yes, ma'am, yes, ma'am, sorry, I wasn't following what you said for a second. Yes, ma'am.
Okay, so we've got a couple caveats here, okay? The first is, we don't have this type of precision. So give yourself a round number for it to kind of be realistic. A couple other caveats. liming rates shouldn't exceed 5,000 pounds of ideal material per acre under tillage. Or, if you're doing no-till, 1,500 pounds at any one time. So we have a lime requirement here of 3,000 pounds of ideal material. If we had that and we were doing no-till, we wouldn't put it all down at once. We would put down about half. Then we would wait a year, we'd put down the other part. If we're tilling in, well then we could put more. All right? So, so in this case where we're going to be applying 8,000 pounds per acre, don't all at once. Apply about half and then apply the other half later on. Yes, yes, sir.
If you're breaking new ground, we plan on using those notes, would you go with notes the initial year or go with the 1,500?
So even if you are no-till.
Ask it one more time.
If you're breaking new ground that's been fallow for a while,
Yeah.
and you're planning on using
So, I mean,
no-till,
Okay.
but it's, you're tilling, like breaking it in the first year, would I use 5,000 the
It'll
first
still
year as a
give
number, or
the number.
I mean, if you're going to be actually disturbing the soil and doing some mixing, then I'd use the larger bag. Yeah, yeah. And if you want to be able to convert between oxides and calcium carbonate equivalent, this SFM5 document that the University of Maryland Extension has, it'll tell you how to do it. All right, so I told you it was more complicated than you want it to be.
Yes.
All right?
I know the 1,500.
But why is it more complicated? It's complicated because you're not living in the real world. You've got a table or a graph. In the case of our University of Maryland document, you got a table that tells you in a real world how much you got to apply. But then you've got a real world product. Chances are you can look it up on that website I've got for you. And you can find the calcium carbonate equivalent given to you. And you can find the details about the sieves, right? And then you're going to follow the formula, and you're going to be able to do it. Are they going to ask you this on the exam? They could. In my experience, will they? No. But don't take that as a guarantee, and don't say, well, Ruppert said it wasn't going to be on there. We're doing this because it could be on there. But it's also good for you to understand, too, because you're going to be consulting people for whom this matters, right? pH matters because we've got to get the pH right in order for our nutrient balances to be right. Lime is required periodically because of those natural acidification that occurs. All right? Okay. Now, we're at time. You've got the remainder of the slides. Now, the remainder of the slides here are pretty important. They have to do with understanding the labels on a fertilizer bag and how you go about using the labels on a fertilizer bag to figure out how much of a particular fertilizer you've got to apply per acre to meet a nutrient requirement. It's pretty important stuff. I guarantee that will be a question or two on the test. Let's go through ultra fast and do some highlights. All right? Okay. You also can email me or call me with a follow-up question. I think my email is at the front of these presentations. Let me give you my phone number. I'll give you my office number. My office number is 301-405-1319. 301-405-1319. So if you've got, as you look at these slides in further detail and you end up with a question, then you give me a call. Okay. This slide is a detail, easy to figure out. We're the University of Maryland. The 4 R's are great, but actually the 4 R's can become the terps, right? timing, rate, placement, and source, but we're going to stick essentials in there. All right? And you can see from the slides what I mean by essentials. And it's a gimmick, but it's also real too. All right? Are nutrients taken up uniformly over the course of a corn crop growing? No. That's why in our recommendations from the university, we provide splits. We say, okay, provide some pre-plant, provide some at planting, and then supply some at side dress, right? Right before this massive increase in the needs for nutrients occurs. Kind of self-explanatory that we would provide this, we would provide our recommendations in splits. And it's true for lots of elements, not just for nitrogen, right? Okay. Enhanced efficiency fertilizers, that's fine. Essentially ways so that we are not releasing all of the nutrients into fertilizer at once, but we're kind of releasing them slowly, different mechanisms to do that, so that we're not basically allowing so many nutrients to get into the ground that there's a danger, that we're heightening the chance of leaching. They're going to be released slowly and basically in timing with the plant. Okay? Lots of different ways to do it. All good stuff. Okay. Let's see here. Okay. Remember, one way to lose nitrogen is through volatilization, right? And so this table here is just telling you if you apply or if you inject manure, you're basically going to keep all of your nitrogen around. None of it's going to volatilize away, or not a lot. But if you rather spread it on the surface and don't till it in for a while, actually most of the nitrogen that was there is going to be gone, and only a fraction of it is still going to be around, useful for the plant. Important thing, there's data behind this. Okay. Cover cropping we've talked about. Legumes that are planted the previous season will continue to give you the gift of nitrogen the following season because of the nitrogens in the residues. Organic nutrient sources applied even 2 seasons previously can continue to give you a gift of residual nitrogen. Table kind of speaks for itself. Go look at that. Now let's talk about rates really fast. This is the part that I want to do with you. All right. Nutrient content of fertilizers. 5, 10, 15. What does that mean? It means this bag contains at least, it will not contain less, 5% nitrogen, 10% phosphate, and 15% potash. It's not the same thing as 10% phosphorus. It's 10% phosphate, P2O5. I've got a table in here that tells you how to convert between phosphorus and phosphate and vice versa. Same thing for potassium. Okay, so what's the contents of this bag? We know it's 5% nitrogen. There's this is a 100-pound bag. So which one of these lines is applicable to this fertilizer bag? D, right? We got a 100-pound bag. At least 5% is nitrogen. So there's our 5 pounds of nitrogen, 5%. 10% phosphate, there's our 10 pounds of phosphate. So D. Tell me about this, so the D's right answer. Tell me about this fertilizer bag. This is not a 100-pound bag, this is a 50-pound bag.
C.
Yes, C, right? We got to half it because we don't have 100 pounds. We now got 50 pounds. Well done. Okay. Why doesn't the fertilizer bag just give me nitrogen, phosphorus, and potassium? Wouldn't that be nice? Okay? Sorry. It's by convention. Okay? And that's just the way that it is. You can think about it this way. Phosphorus and potassium are mined, so they're kind of minerals in a way. And so therefore we kind of give an oxide, we give them as oxides. That's the way to think about it. But here's the funny thing. There ain't actually no such thing as P2O5 in real life, right? That's a convention that's inherited from something that happened probably in the 17th century. We're still living with it. Can we convert between that and phosphorus? Yes. Is it that hard? No. All right? But it's by convention. We just decide to live with it. Okay, here's how you do that. If you want to convert from phosphorus to P2O5, multiply by this, right? If you want to convert from P2O5 to P, multiply by that. All right? You're good. You got this slide. All right? I don't know whether they give you those conversion factors for the exam or not.
No.
Yeah, you might have to. Okay, so you got to know. You got to know how to do it. Now, it ain't so bad because 1 divided by 2.29 is what? 0.44, right? And 1 divided by 1.2 is 0.83. So these are inverses of one another. Here's a slide. I'm not going to go into detail about it, but this shows you how this works, okay? This is the math that is the justification behind those numbers. We're starting off with a periodic table, all right? And then just follow it. You got the justification for where do we get 2.29, all that stuff, all right? This was for potassium. Here it is for phosphorus. So look at that at your leisure. If anything doesn't make any sense, give me a call. All right. That's a whole bag of stuff. Why does it only contain 30% of what I might want? All right? Well, think of muriate of potash. The only thing that's in there is, you think the only thing that's in there is potassium. But remember what potassium here, positively charged, okay? There's no way you can get a bag of purely positively charged material. Reality is neutral. So there's got to be some negative thing attached to it that makes the whole thing neutral, and that's chlorine. So the rest of the stuff is chlorine. You don't necessarily want that. Okay? So here's some tables that just shows you, you might be getting nitrogen in the form of ammonia, but there's some hydrogens along with it, and that's why it's not 100. Okay? Et cetera, et cetera. There's just other stuff that comes along. For phosphorus materials, right? For potassium-bearing materials, et cetera, et cetera. Okay. This is an important one. So pay very close attention. This will definitely be on the test, for sure. All right? Let's say that you've got a recommendation where you need to apply 90 pounds per acre of potash. Phosphorus isn't recommended. Nitrogen's not recommended. Let's say that you've got muriate of potash to do that with. How much muriate of potash per acre should be applied? First thing you do is you open up your calculus book to page 1500, do whatever it says, and do this incredibly complicated calculation. All right? You're going to take your recommendation, 90 pounds per acre, and you're going to divide by the decimal percent of the content of the bag. One divided by the other. It's as easy as it really could be. So here's your recommended amount, 90 pounds per acre. You're going to divide by the potash content of your product, and you're going to get the application rate. So here's that formula. The requirement divided by the decimal nutrient content of the product. We're not dividing by 60%, we're dividing by 0.6. And we're going to get the amount that we need to apply per acre. And if you're interested in why the units work out like that, here's how the units work out, if you want to see the details. If you got a question for me, you can give me a call. All right? Will this be on the test?
Yeah.
Yes, it will be on the test. This is an example with potash, but you can invent an example with nitrogen, you can invent an example with phosphate, P2O5. That's what I wanted to get through with you, because it's very important. I'm sure it's going to be on there. The nice thing is, it's not so bad. We got the formula for you, and we got how the units work out. Okay? This might be on there. This is a little bit more complex, but it says that this could be a question. What's the nutrient content of something like that? All right. What's the nutrient content of that mineral? Well, here's what we're going to do. We're going to take from the periodic table, you know, the grams per mole of whatever the contents are. Expect that they would give this to you. Then we wonder, from that chemical formula, how many moles of that element are there per mole of the mineral, right? There's one calcium atom there, so that's one. One potassium, one phosphate, and 4 oxygens. And then we're just going to multiply. And so
What's the total mass?
that's the total mass. And then what I'm going to do is I'm going to take 39.1 and divide by 174.1, and I'll get 22. That's for potassium, but I really want it in terms of potash, right? Because that's how I do it. So then I'm either going to divide by kind of that conversion that I showed you on the previous table, or I'll multiply by the inverse of it, and I'll get my answer the equivalent of potash. I get this 18. That's 30.97 divided by 174, and then I'll use those factors on that table I showed you before, and I'll do that. They didn't have this on the exam from last year. They probably won't ask. But that's how to do it. Okay. So that's the important stuff. This is the one you want to be able to do. Okay? All right. Over time, we want to keep rolling. If you've got any questions, look in your, give me a phone call or send me an email. Okay? All right.
Do we want to take a 5-minute break instead of our 15? Is everybody okay with that? And then we'll just keep rolling?
Sure.
Awesome. So we will touch base at 2:50.
Really?